Alright, so let's consider the question. The question says an oil of specific gravity 0.85 and viscosity 0.1 Newton seconds per meter squared is formed through a 3 centimeter diameter pipe. If the pressure drop per meter length of the pipe is 15 kilopascal, question says find A. Mass flow rate in kilograms per minute, B. The shear stress at the wall of the pipe, C. The velocity at a distance of 0.5 millimeter from the pipe surface, and finally D. The power required to maintain the flow. Alright, so let's start with selecting our parameters. The question says an oil of specific gravity, so indicate specific gravity. Okay, S was given as 0.85 and viscosity 0.1 Newton seconds per meter squared. So take note, when the viscosity is expressed in Newton seconds per meter squared, it is actually dynamic viscosity. Okay, so we have dynamic viscosity. Dynamic viscosity mu is 0.1 Newton seconds per meter squared. Alright, it's pumped through a 3 centimeter diameter pipe. So diameter of pipe was given. Diameter D equals 3 centimeter. We simply convert this to meters by dividing 3 by 100, and this equal to 0.03 in meters. Alright, so the question next parameter says if the pressure drop per meter length. So pressure drop per meter length simply means pressure gradient. Okay, pressure gradient. Okay, and that is dp all over dx, where dp means change in pressure, dx means change in length. So it's called pressure gradient and is given as 15 kilopascal. So we convert this to pascal per meter simply by multiplying through by 1000. Okay, kilo is 1000, so this becomes 15,000 pascal per meter, because it is actually dp dx, so become 15,000 pascal per meter. Alright, now the first question says find the mass flow rate. How do you find the mass flow rate? Mass flow rate is given as, okay, m dot is simply density times discharge. This gives us mass flow rate, but if you're confused and you want to know how, the unit of density is kilograms per meter cube multiplying by unit of discharge. Discharge is meter cube per second. So notice that meter cube cancels meter cube. You're left with kilogram per second, which is actually the unit of mass flow rate, which is mass of free fluid within a given time. So we simply have density times gravity, times discharge. Now, how do we find density? We were given specific gravity. Recall, specific gravity S is simply density of the oil all over density of water. So which means this implies in order to find density of this oil, all you need to do is cross multiply specific gravity multiplies density of water. So I have density of oil to be equal to specific gravity times density of water. So this is how we are able to compute or find the density of that oil. So density of oil is equal to, specific gravity was given as 0.85 multiplied by density of water is constant, which is 1000. So this implies that the density of the oil is equal to 850 kilograms per meter cube. So you keep this aside. Alright, so in order to find mass flow rate, we have to find density and we have to find discharge. So we found density. The next thing now is to find the discharge. Now, in order to find discharge, we make use of the Hagen Poisuilles equation. Okay, we make use of the Hagen Poisuilles equation. So from Hagen Poisuilles equation, we have that the change in the pressure gradient, which is dp all over dx, is equal to 8 times dynamic viscosity times discharge all over pi r to the power of 4. So this relates the pressure gradient to discharge. Okay, so it means that in order to make discharge the subject of the formula, this simply implies that discharge is equal to, we simply cross multiply the whole of this, dp dx multiplies pi r4. So we have dp all over the x, which is the pressure gradient, multiplied by pi r to the power of 4 all over, we divide through by what, 8 mu, all over 8 mu. So this will give us the discharge. Alright, so from here now you can obtain that discharge Q is equal to, we have dp dx, which is the pressure gradient, and from the question, pressure gradient was given to us as what, 15,000 pascal per meter. So this simply becomes 15,000 multiplied by pi is 3.142 multiplied by radius to the power of 4. But now we were given diameter, not forgetting diameter was given as 0.03 in meters, and we know that radius is simply diameter all over 2. So we can find the radius using this equation. Diameter is 0.03 divided by 2, which implies that the radius of the pipe is 0.015 in meters. So this gives us the radius of the pipe. So if we have this as the radius of the pipe, then let's fall back to this equation now. So we have dp dx, which is 15,000 multiplied by pi remains 3.142 multiplied by radius to the power of 4, and radius is 0.015 all to the power of 4 all over, then we divide through by 8 mu. So this is 8 multiplied by mu is dynamic viscosity, and from the question mu was given as 0.1 Newton seconds per meter squared. So simply multiply 0.1. Alright, so let's flip over and see what we're going to obtain. So let's calculate the numerator. Discharge is now equal to, discharge Q is now equal to, let's calculate the numerator from what we have there. Okay, numerator says 1,500 multiplies 3.142, sorry, 15,000 multiplies 3.142. Numerator says 15,000 multiplies 3.142, 15,000 multiplies 3.142 multiplied by radius to the power of 4, which is 0.015 to the power of 4. Okay, that gives us 2.3860 by 10 to the power of minus 3. So we have 2.3860 by 10 to the power of minus 3 all over, then for the denominator we have 8 multiplied 0.1, that will obviously give us 0.8. Alright, so let's now obtain 2.3860 exponential minus 3 divide 0.8. Alright, so that simply gives us 2.98 by 10 to the power of minus 3 in meter cube per seconds. So this becomes discharge. Now recall earlier I said that to calculate the mass flow rate, all you need to do is simply multiply density and the discharge. Now we've obtained the density to be 850, we've found the discharge, so we can now find the mass flow rate. Therefore, mass flow rate m dot, we said is density is 850 multiplied by discharge is 2.98 by 10 to the power of minus 3. So this simply implies that mass flow rate m dot is now equal to, so the mass flow rate gives us 2.533 kilograms per seconds. But not forgetting, the question says calculate the mass flow rate in kilograms per minute. So we have to find this in kilograms per minute. So you recall that 1 minute is equivalent to what? 60 seconds. So in order to convert this now becomes that mass flow rate is equal to, we have 2.533, this is kilograms per seconds, multiplied by, now recall, 60 seconds make what? 1 minute. So from here, seconds cancel seconds, you're left with minutes on the net here. So this is now equal to 2.533 multiplied by 60. Okay, remember your units, kilogram is here, kilograms all over, whereas I have 1 minute here, so all over minutes. So we simply compute 2.533 multiplied by 60, and this implies that mass flow rate is equal to 2.533 multiply 60. That gives us 15.198 kilograms per minute. So this is the first question answered. So that's the mass flow rate in kilograms per minute. Now the next question says we should calculate the shear stress at the wall of the pipe. Now to calculate the shear stress B, shear stress at the wall of the pipe. Alright, so now you simply use equation tau is equal to 4 mu V all over D to calculate the shear stress. So all we need to do is what? Find V, which is the velocity. We know the diameter, of course. Mu stands for dynamic viscosity, we also know it, and this is what we're looking for, the shear stress. But then, how do we find velocity? Recall that discharge Q is area times velocity. So which means, and we've already obtained the value of the discharge earlier. Okay, we saw for discharge earlier to be this. Okay, this is our discharge Q. We saw it to be this 2.98 by 10 to the power of minus 3. So all we need to do is, since we know our discharge, we can find the area of the pipe. Okay, therefore, first of all, velocity from this equation becomes discharge all over area. Velocity is equal to discharge all over area. So let's find the area now. Recall that area is pi d squared all over 4. This is now equal to pi is 3.142. Okay, pi is 3.142 times diameter was given to us as 0.03. Okay, all squared divided by 4. So I will compute all of this together and obtain answer just to save time. So if you do all of this together, you have area to be 7.0695 by 10 to the power of minus 4 in meters squared. So this becomes the area. So if this is the area, simply put into this equation to obtain the velocity. Therefore, velocity V is equal to, we said, discharge all over area, and discharge was given to us earlier. We saw for discharge to be 2.98 by 10 to the power of minus 3. So this becomes 2.98 by 10 to the power of minus 3 divides the area, which is 7.0695 by 10 to the power of minus 4. Alright, so this simply implies that velocity V is now equal to, so let's compute this, 2.98 exponential minus 3 divided by answer. That gives us 4.2 meters per second. So this becomes the velocity of the fluid. So if this is the velocity of the flow, then we can now compute the shear stress using this equation which I stated earlier. Alright, so therefore shear stress tau is equal to, we said, 4 multiplied by mu, and mu was given to us in the equation, that's dynamic viscosity as 0.1 multiplied by velocity, which we just obtained now, 4.2 all over d, which is diameter. Diameter means 0.03. So this is now equal to, I'll do everything as well. So I have here 4 times 0.1 multiplied by 4.2 divides 0.03. So that gives us the shear stress tau. This implies tau is equal to 56 newtons per meter squared, or you can simply say 56 pascal if you wish. So this becomes the shear stress of the fluid. That's the second question answered. Now the third question says the velocity of the fluid at a distance of 0.5 millimeter from the pipe surface. Okay, velocity of fluid at a distance of 0.5 millimeter. That's question C. Velocity of fluid at a distance 0.5 millimeter from pipe surface. So to solve this, we make use of the Hagen Poisuilles laminar flow equation. From Hagen Poisuilles laminar flow equation. Alright, the equation simply says that the velocity at a distance, in this case r, because the distance is the radius of the given pipe given to us, 0.5 millimeter. So since it's a pipe and it has diameter, it means distance becomes radius along the radial axis. So from Hagen Poisuilles equation, Vr, or velocity at a distance, is simply equal to dp dx, which is the pressure gradient, multiplied by 1 all over 4 times dynamic viscosity mu, multiplied by r squared minus r squared. Okay, so I have this where r squared becomes the radius of the larger pipe, and then the smaller r squared becomes the radius of the where the bigger r squared stands for the radius of the outer diameter pipe, and then the smaller r squared stands for the radius of the internal diameter pipe, which is now the distance of the pipeline given to us, in this case 0.5 millimeter. So we need to convert this. Okay, alright, so this becomes the radial arm 0.5, which is the internal radius of the pipe. That's the distance traveled from within the internal inlet of the pipe. So we are to now look for our velocity at this distance, where r squared becomes the radius of the larger diameter. Okay, so we already obtained r earlier. We already obtained r earlier. That's the radius of the pipe, the bigger radius, to be equal to 0.15. Alright, so here we already obtained r to be 0.15 here, 0.015. That's the radius of the larger pipe. So r has already been obtained as 0.015 in meters. Now the distance, this is now a radial distance, r, which is a smaller r, was given to us in the question. It said calculate the velocity at a distance of 0.5 millimeters. So that becomes the radial distance, 0.5 millimeters. So converting this to meters, as you have to divide by 1000, that will give you about 0.005 in meters. So you have that to be 0.005 in meters. That gives you the radial distance. So if you have this now, all you need to do is to calculate the value for using the Hagen Poisuilles laminar flow equation, which I gave earlier. Okay, using the Hagen Poisuilles laminar equation, which I gave earlier, which is this. So we can now find the velocity. Therefore, velocity at that distance 0.0005, is now equal to, so we said here it is the pdx, or the pdx here, which is pressure gradient, and pressure gradient was given to us as 15,000 multiplied by 1 all over 4 times dynamic viscosity. So we have 1 all over 4 multiplied by 0.1, okay, times the larger radius squared, and the larger radius give us 0.015. So we have 0.015 all squared minus the smaller radius, which give us 0.0005 all squared. So I have this. Alright, so this implies that velocity at 0.0005 is now equal to, so this is simply 15,000 all over 4 times 0.1 gives us 0.4 into, so let's obtain 0.015 squared. So we find 0.015 squared. So I'm going to do this together. 0.015 squared minus 0.0005 squared. I'll do all of them together. 15 squared minus 0.0005 squared. So this gives us 2.2475 by 10 to the power of minus 4. This gives us 2.2475 by 10 to the power of minus 4. Alright, so I'm going to multiply through by 15,000 and then divide by 0.4. That will give us the velocity at that distance, 0.005. So we have this to be equal to multiply by 15,000 divide 0.4. So the velocity at this distance gives us 0.43 meters per second. That becomes the velocity at that distance. Alright, finally, the final question says calculate the power required to maintain the flow. Power required to maintain the flow. That's question D. Power required to maintain the flow. Alright, to do this is simple. The equation for power, P, is simply equal to specific weight multiplied by discharge multiplied by head loss due to friction. So this is actually the power is simply specific weight multiplied discharge multiplied by head loss due to friction. So all we need to do, we already know our discharge. Of course, to calculate the specific weight is also not a problem. All we need to do is what? Find the head loss due to friction. But let's do them individually. Specific weight, specific weight, which is small w, is simply density times gravity. So density of the oil times gravity. And we solved earlier, we obtained the density of the oil to be 850, not forgetting. So we have 850 multiplied gravity is 9.81. So this will give us the specific weight of the oil. So 850 multiplies 9.81. Alright, next thing to do is to find the, we've already found the discharge, so we need to find the head loss. Now to find head loss, we make use of the Daicy-Weisbach equation. We make use of the Daicy-Weisbach equation to find the head loss. So head loss due to friction, HF, is simply equal to, from Daicy-Weisbach, is giving us 4FL V squared all over D times 2G, where F means the coefficient of friction or the friction factor, and it depends on the Reynolds number. L stands for the length of the pipe. So we have a V squared all over D times 2G. Alright, so in order to calculate the friction factor, we make use of the Reynolds number. The friction factor depends on the Reynolds number. Where F, first of all, calculate Reynolds number is equal to rho VD all over mu for the Reynolds number. So Reynolds number is equal to, rho is density, in this case now density of the oil, which is 850 multiplied by V, and V remains the velocity of flow of the fluid. So recall earlier we calculated the velocity of the fluid and we obtained 4.2 meters per second square for the velocity. So we simply impute that into the equation for Reynolds number. So we have it. So in place of velocity, we simply multiply 4.2 meters per second to the diameter of the pipe. Diameter of the pipe remains 0.03. All over dynamic viscosity, which was given to us as 0.1. 1. So let's obtain the Reynolds number now. So I'll do everything at once and get a value. So computing everything will obtain the Reynolds number to be 1071. Now since Reynolds number is less than 2000, since Reynolds number is less than 2000, it means to find the friction factor F, we simply employ 0.16 all over Reynolds number. So because the Reynolds number value is quite less than 2000, so in order to calculate for the friction factor, we make use of the equation. Alright, therefore friction factor F is now equal to, so we said 0.16 divided by the Reynolds number, which is 1071. So this implies that the friction factor is equal to, so we have F to be 1.5 by 10 to the power of minus 4. This becomes the friction factor. So we plug it back into the equation for the head loss due to friction. Therefore, head loss due to friction is now equal to, we said 4 multiplied by the friction factor, which is 1.5 by 10 to the power of minus 4 multiplied by the length. Now, the length is always taken as 1 since you're giving pressure per meter length, so it's taken as 1. Alright, multiplied by the velocity of flow, which we got earlier as 4.2, in this case now 4.2 squared, all over diameter of the pipe remains 0.03 multiplied by 2 multiplied by g. G means 9.81, which is gravity. So I'm using this equation for Daicy-Weisbach. Sorry. So multiply by 9.81. Okay. So as usual, I'll also point. Okay, let me point the numerator first. 4.2 squared multiply 1.5 exponential minus 4 multiply by 4. So you have 0.010584 all divided by, so let's obtain the denominator. 0.03 multiplied 2 multiplied by 9.81 multiplies 2 multiplies 9.81, that gives us 0.5886. Alright, so let's obtain that division now. 0.010584 divided by 0.5586. That gives us the head loss due to friction to be equal to, so we have the head loss due to friction to be equal to 0.017180, okay, 0.0180 in meter. This becomes the head loss due to friction. So if you have this as a head loss due to friction, we can now find the power required. Therefore, power, we said, is simply specific weight multiplied by discharge multiplied by head loss due to friction, and we've obtained specific weight earlier. We saw for specific weight as 8338.5. This is actually 8338.5, please. So power is equal to specific weight 8338.5 multiplied by discharge. We already obtained discharge earlier in our solution. Okay, we obtained discharge as 2.98 by 10 to the power of minus 3. So multiplies 2.98 by 10 to the power of minus 3 multiplied by, okay, multiplied by head loss due to friction, and we obtain that here at 0.0180. Alright, so this will give us the power required to maintain the flow. So let's multiply everything all through. Multiply by 8338.5 multiply by 2.98 exponential minus 3 that gives us 0.45 in in. Alright, so this is the power required to maintain the flow. Alright guys, so that's the end of that given question. I will see you in the next video with another question on fluid dynamics. Thanks and cheers.